Dear students, next unit arch. So arch is predominantly a compression member subjected to perpendicular loads. The perpendicular loads are transferred from the deck slab in the vehicular bridges. So this element is called as spandrel beam. It transfers the load from deck slab and to the arches so that the arch will have UDL or point load combinations in its surface. So normally the types of arches are polygon, circular, parabolic, elliptical, or any curved shape can form a arch geometry. And the types of materials used are masonry, RCC, and steel. So the masonry structure is very old, which is nowadays obsolete, and we can classify the arches depending upon the number of hinges present. If it is simply supported, this end is assumed to be hinged. Simply supported means the bending moment is zero, so it is otherwise called as hinged support. In addition to the two supports, if you have a hinge at its crown point, the topmost point is called the crown. If it is having a hinge means this type of arch is called three hinged arch. If you are having a hinge at the support level only, the support level is simply supported, so it is has having two hinged. It is having two hinged. So if you add one hinge in the arch profile, your calculation will be very much easier to find out the unknown reactions RA, RB, and the horizontal reaction because three number of unknowns. So three number of equations we will have. Bending moment at A equal to 0, bending moment at B equal to 0, and bending moment at C equal to 0. So three number of unknowns and three number of equations. So this type of structure is very much comfortable to analyze, but in practical it is very much inefficient. It will lead to complete collapse by forming the mechanism. Before the failure, this hinge will form a mechanism for its sudden collapse. So, establishing a hinge point in the arch is not advisable. The fixed arch will be there. The masonry arch is oftenly called as fixed type of construction, arch construction. And the supports are will be called as springings. Springings means supports, support levels. So the load transfer is from deck slab to spandrel beam to arch, the arch to supports. And one special type of arch is there, that is linear arch. Linear arch is not at all is not only the type of arch, it is a concept. It is a concept. Linear arch, otherwise called as line of thrust, otherwise called as funicular arch or funicular polygon, or otherwise called as theoretical arch. Theoretical arch. We are not having practical availability, so it is assumed to be theoretical arch. Why it is assumed to be theoretical arch means generally the arch profile will be like this. That is a curved surface. But here we are assuming if you are applying a load W, we can make two components perpendicular to the arch profile, so W1 and W2. If you connect this line of action to this support and this line of action to the right support, you are naming with A, C, and B. The line of thrust of W1 and W2. If you make the arch profile like this, for the application of load W, it will be very much comfortable for the load transformation. But it is not practically available. So it is hence it is called theoretical arch because these two components W1 and W2 will be transferred along CB and AC respectively. If you connect the number of point loads like this, number of point loads like this with the support condition, you will have the funicular arch type. That is, you connect with the straight line, then connect with the straight line, then connect with the straight line, then connect with the straight line, and for the straight line. So the arch profile will be like the line of thrust. The arch profile will be like line of thrust. Okay, so we will have the load W1 here and W2 and W3 and W4 and W5, and these are the support conditions. So this will lead to the type of arch like this, which is called theoretical arch or funicular arch or line of thrust or linear arch. Here the tensile force will be traveled like this, okay, T1, T2 up to T3, T4, T5 and T6. So this is a concept of linear arch. If you connect the components of applied load with the support levels, you will have a triangular pattern of load transferring, linear transformation of the load. If you connect multiple point loads like this, you will have the linear arch. So it is only theoretically defined. Okay. In arches, we are going to calculate. I am going to first of all explain with the three hinged arch because it is comfortable for the calculation. So A, B, and C. So the normal unknowns, regular unknowns, that is RA, reaction at A, reaction at B, and horizontal thrust at A and B. If your load is symmetrical with the perpendicular load and there is no horizontal load, then your H will be same and the supports are at same level, then H will be in the same line of action. Then I have mentioned as H instead of H1 and H2, it is equal H. So the arch action is you are applying the perpendicular load on the surface of the arch so that this arch will sag. This arch will sag. Due to the horizontal reaction developed at the support, it will lead to hogging type of bending. The applied load will lead to sagging type of bending, whereas the created horizontal thrust will have hogging type of bending. So this sagging type of bending will be contracted by the hogging type of bending so that the net bending moment at any particular section will be lesser than the normal. That is called arch action. That is the advantageous concept of using the arch. The net bending moment will be minimum because of the horizontal thrust. Because if you are taking moment about any section, this perpendicular load will be rotating like this and the horizontal thrust will be rotating in the opposite direction. So the applied load will be resisted by the horizontal thrust. Okay, so this is called arch action. And other than this RA and H, we will have normal thrust and radial shear. Normal thrust and radial shear because of the curved element. We are calculating normal thrust and radial shear at the particular section. And if you want to calculate the bending moment here, mx, the normal calculation is the bending moment at this point I'm considering as mu x means the mx at this point x is calculated as mu x is the bending moment at that point, bending moment at that point due to the applied load W. So it will be rotated like this and H will be rotated in the opposite direction. The H should have some perpendicular direction up to the section that is meant by Y. So mu x minus Hy. So the bending moment at a particular section is equal to the bending moment at this point due to the vertical load minus H into Y. And at the crown point is the hinged point, three hinged. So it is a hinged point where bending moment equal to 0. So we have bending moment equal to 0 at A and B and C. So with the help of these three equilibrium conditions, we can calculate the available unknowns. Next, in parabolic arch, we are going to first analyze the parabolic arch. Parabolic arch. So consider the section, support level, and the section from the left support is x. So the equation of parabola from the support level, because we will have the equation of parabola different from the crown level. So I am going to write equation of parabola from the support level y equal to 4 yc means depth of crown point and the L means span, x is the distance from the left support. So this crown distance is yc, x is the from the left support and total length is L. The equation of parabola y equal to 4yc by L square x into L minus x. This is the equation of parabola. So we can have some point here. At this point, the deflection is 0. There is no deflection because of the support condition. At this point, the deflection is 0. At x equal to L, y equal to 0. At this point, there is no slope. There is no slope. So, x equal to L by 2, dy by dx is equal to 0. dy by dx equal to 0. We can prove the slope is 0 at the crown point from this equation. We have, if you are substituting x equal to 0, then definitely y equal to 0 from this equation. If you are substituting x equal to L, then also y equal to 0. Now I am differentiating this equation 4yc by L square. You multiplied with x inside and differentiate. So it will leads to this equation. If I apply x equal to L by 2, dy by dx equal to 0. Then I'm going to substitute x equal to L by 2 here. 4yc by L square, L minus 2 into L by 2. So L minus L will be equal to 0. Then dy by dx equal to 0. So it has proven that at the crown point, the slope is equal to 0. From this parabola type of arch, we can prove the slope at the crown point equal to 0. Then I am going to explain the normal thrust and radial shear from this point. You consider the cross section of arch and the perpendicular line and the radial line. You can divide the segments perpendicular to the plane of the arch as well as normal and horizontal axis. I can define the slope of this line. I can define the slope of this line. Okay. The angle between this sloped line to the horizontal is theta, so that this is 90 minus theta, and further this is theta, here 90 minus theta, and here it is theta, and 90 minus theta, and 90 minus theta. We have completed up to 360 degree. Now I am going to represent the various parameters. So this is in the radial direction. Normally the Vx will be in this direction and Hx will be in this direction, and the normal to the plane, this is the normal line. So the normal to the plane of the axis is Nx, okay, and along the radial line it is Rx. Along the radial line it is Rx. So we are going to calculate Nx and Rx with the help of Hx and Vx, because from the given geometry we can easily find out the vertical reaction and the horizontal reaction. From Hx and Vx we can calculate Rx and Nx. Rx is the radial shear. Rx is the radial shear. So which is equal to, so you completely rotate the Hx and the Vx in the direction of Rx. How we can rotate? You can rotate along this direction Hx and Vx along this direction. So Hx and Vx is both are opposite, because Hx if you rotate it is downward direction, Vx if you rotate it is upward direction. Here the angle is theta, here it is 90 minus theta. If you put cos angle to this theta, 90 minus theta is the sine angle. So I can write Vx cos theta minus Hx sine theta, that is Rx. Next one, Nx. Nx is the normal thrust, which is equal to, you rotate all these forces along this direction, Vx as well as Hx. If you rotate Vx along this direction and Hx along this direction, both the component will have same direction. So both the component will have positive quantity, and Hx is comprising of angle theta and Vx will comprising of 90 minus theta. So theta is along with cos, 90 minus theta is the sine component. So Hx cos theta plus Vx sin theta. So you can remember as the formula, or otherwise you can understand the components and direction. You can easily derive this formula. So the arch problem will be very simple to calculate for exam point of view. For 16 marks problem, it is very simple. Now we are going to have a simple problem proving the bending moment along the arch profile is zero for the loading condition of UDL, because normally a simply supported condition uh, with the UDL W Newton per meter, will have the bending moment as WL square by 8. So this profile is the parabolic profile. This profile is the parabolic profile. If you are loaded an arch with this UDL throughout the span, you will definitely get the bending moment to zero, because the arch is type of, if you consider the parabolic arch in that case, you will have the definitely the bending moment zero, because you are providing the arch profile in the same shape as the bending moment of the simply supported with the UDL. So both are contracting and the net bending moment will be zero. In general case, if you are providing a profile same as bending moment diagram, then the bending moment will be zero. So consider this problem. a three hinged parabolic arch of span L and rise H carries an UDL W per meter run throughout the span. Show the horizontal thrust at each support is WL squared by 8H, and also the bending moment at any point of arch is 0. Actually, H is small h because the height of the arch, that is rise of the arch, is small h. So it is W squared by 8h. So let us consider it is a three hinged arch. So hinge at the supports and at the crown point. The h is the rise. We have VA and H due to only the vertical load present in the arch. So H is same both the supports. The load is UDL W per meter run throughout the um, span. And what are the possibility of calculating the VA and VB? Taking moment about A, taking moment about A, that is MA equal to 0. So VB into the span is L, the span is L, VB into L, so it is rotating in this direction, load is rotating in the opposite direction, minus W into L square by 2 equal to 0. So VB equal to W L by 2. Otherwise, we can simply calculate the total load is equal to W into L. W into L is the total load. The load is symmetric, so VA as well as VB equal to WL by 2. That is total load by 2. So we have calculated VA and VB. For the calculation of H, taking moment about the crown point, taking moment about crown point, that is moment about C equals 0. I can refer it as C, moment about C equal to 0. So VA into half of this span, it is L by 2. VA into L by 2 minus VA is rotating in this direction, H is rotating in the opposite direction. So H into YC, actually the rise distance is small h. VA into L by 2 minus H into small h, and the load is also rotating in the same direction as H. So minus W into L by 2 is the span and L by 2 of half, that is half of the distance, equal to 0. If you are introducing a hinge at this profile, you can separate as a two section. You can separate as a two section up to the hinge point and you can analyze separately. That's what we have done. W per meter. So this is VA. We are having H. The span is L by 2 and rise is H. So W into L by 2 and half of L by 2, which is equal to 0. So VA equal to WL by 2 into L by 2 minus H into H minus W into L square by 8 equal to 0. You bring this term to the right side. H into H equal to WL square by 4 minus WL square by 8. Taking LCM 8 to WL square minus WL square, which is equal to WL square by 8, which is equal to H into H. So that capital H is the horizontal thrust, which is equal to WL square by 8H. So this is the first question. Find out the horizontal thrust, which is equal to W square by 8h. And also for prove that bending moment at any point of arch is zero. Bending moment at any point of arch is zero. Now we are going to write the bending moment equation at any point. So I'm going to consider this point, which is x distance from the left support. Our equation y equal to 4. Yc is the rise or crown height by L square x into L minus x. So I am substituting 4 into yc equal to h by L square, and also I am going to multiply x inside Lx minus x square. So keep this will be used in the bending moment equation. So I am going to write the bending moment at this section x6. So mx equal to, we are having Va and the h and the loading up to the section x6, that is W per meter. So mx equal to Va into x, it is rotating in this direction, minus h into y. I'm mentioning the vertical distance equal to y because this is not the crown point, this is somewhere else. The crown point distance only small h. So other distances, vertical distances can be mentioned with y. So Va into x minus h into y minus this load as well as h will be rotating in the same direction. So W into x square by 2. So VI is W L by 2 into x minus h is equal to, we already found that W L square by 8h, and y you can substitute this term, that is 4h by L square Lx minus x square minus wx square. We are going to simplify this equation and mm, L square cancel. Okay, h cancel. 4 8 2 times. So wlx by 2 minus w by 2 into lx minus x square minus wx square by 2. Then WLX by 2 minus WLX by 2 plus WX square by 2 minus WX square by 2. All terms get cancelled, which is equal to 0. Hence, it is proven that the bending moment is 0 at any point of parabolic arch subjected to and UDL throughout the span. So with this understanding, we can continue more problems in this topic. Thank you.